What's up YouTube? Mr. Salotkar back at it again with another video. In this video, I will be going over the process of writing formula of a chemical compound from a given name. Grab a notebook and a pen, some headphones, and let's learn some chemistry. Early warning though, this video might get a bit long because there's a lot to cover. So let's begin with writing formulas for covalent compounds, because writing formulas for covalent compounds is a lot simpler compared to some of the ionic compounds. So in front of you is phosphorus pentachloride. Phosphorus is simply P, and we have learned already that penta refers to 5 and chloride refers to Cl. This tells us that pentachloride means 5 chlorines, and so all you have to do is put Cl followed by 5, and that is all there is. Like I said, covalent compounds are really simple. All you have to know are your prefixes. You should already have those in your notebook, and if you don't, a quick Google search will give you all the prefixes. So this is phosphorus pentachloride. Let's take another example of dinitrogen tetroxide. So you have two prefixes here. You have the prefix di, which means 2, and then you have the prefix tetra, which means 4. And the di prefix is with nitrogen, and the tetra is with oxygen, and that would give you N2O4. Again, you just take the prefix and the element, prefix and the element, and write them together. Here's the most important thing you have to remember. When you write formulas for covalent compounds, there's going to be 2 nonmetals. Always. And so you take these 2 nonmetals and you pair them with their subscripts, and there you go. That's your formula for covalent compound. On the next slide, I'm going to write down names of some chemicals. Try them in your notebook and see if you get the right answers. So before we deep dive into the process of writing the formulas of ionic compounds, there is a very important concept we need to learn, and that is called oxidation numbers. So let's define an oxidation number. So here's the definition, and as you must have expected, there are elaborate rules on how to assign oxidation numbers to specific atoms. But for the sake of this video and this particular topic, we are not going to dive into those rules. That is a topic for another video. For now, we just need to know that oxidation numbers are found from the periodic table. So then what exactly does this definition mean? It means that if you have a sample of, let's say, sodium, right? It's a block of sodium. You've seen it before. It's that shiny silvery metal thing that we blew up in water. Now, this block of sodium, if it had entirely been made out of ions instead of atoms, every single atom of sodium would contain a positive charge. What does this positive charge mean? It means that it lost 1 electron. And that's how it got to have the positive charge. Turns out, every atom in the group 1A element has a 1 positive oxidation number. Every element in 2A has a 2 positive oxidation number. 3A is 3 positive. Then you skip 4A, you go to 5A, and this is where you start getting your anions. And because you are making anions, which is what you get when you gain electrons, now you have 3 negative, 6A is 2 negative, 7A is 1 negative, and then finally 8A is 0, because if you remember, 8A is the noble gases, and noble gases already have 8 electrons, so there is no need for them to either lose or gain electrons. Now you must have noticed that I left out all the B group elements. Those are our transition metals. Turns out, transition metals don't have a fixed oxidation number. Now what exactly does this mean? I will explain by taking an actual example. So let's use what we've learned so far and apply that to solve an actual problem. So in front of you is an example of magnesium chloride. Magnesium chloride is an ionic compound. You know that because the first word in this name is a metal, so it must be ionic. Also, notice that this is a binary compound. How do we know this is binary? Because it has one part metal and one part non-metal. How do we know that it's only one part non-metal? See what it ends with. It ends with "ide," which means that there's only one of each kind. Now, let's figure out the formula. So once you've figured out that this is a binary compound, you note down the formulas or the symbols of these two elements. Magnesium being Mg, and chloride, which is chlorine, is Cl. Now that you have the formulas down, you find these two elements in the periodic table. When you look through the periodic table, you will notice that magnesium belongs to group 2A, chlorine belongs to group 7A. And now that you know their group numbers, you will then know that this is 2 positive and chlorine is 1 negative. Now at this point, you have 2 positive charges on magnesium and 1 negative charge on chlorine. Your job is to balance these out so that if you add these 2 charges together, you should get 0. So in order to cancel out these 2 positive charges, we're going to need 1 more negative charge. And that leaves you in a situation where you have 1 atom of magnesium. So this is 1 atom with 2 positives, and these are 2 atoms, each with 1 negative. And as a result, the formula then becomes MgCl2. It is very, very important that you remember that the final charge of this molecule has to be 0. Always. Let's take another example of sodium sulfide. And we know that sodium is Na, and sulfide, because it ends with ide, IDE, it must be an element, not a polyatomic ion, and so sulfide comes from the element sulfur. Your next job is to find these in the periodic table, and you will notice that sodium is 1 positive and sulfur is 2 negatives. Your last goal is to balance these out. When you add them, they must equal 0. So you add another atom of sodium, and that should give you the formula Na2S. And this is the formula of sodium sulfide. I cannot stress this enough. The minute you identify the name in front of you, like this one for example, is ionic, then you have got to balance your charges. If you don't balance your charges, you will not get the right formulas. on to our third example. Remember, we're still under binary compounds. The thing with ionic compounds is once you understand how binary compounds work, learning about tertiary compounds is going to be really simple. So please make sure that if you're not understanding this, go back and watch the video again and try to solve some problems on your own. If you still have doubts, please ask your teacher. So the formula in front of you is that of iron 2 oxide. The eagle-eyed among you must have noticed that we have introduced a new player in this problem, and that is that Roman numeral 2. That Roman numeral 2 is very, very significant. It is extremely important. It is going to help you get the right formula. Roman numerals are only applicable to transition metals. Okay, so they're only used for B group elements. The first two problems we did, where we had, I think, sodium and magnesium, and we did not use the Roman numerals because those two were A group elements. This iron is a B group element. Now, if you recollect, I did not tell you the oxidation number of iron. So we know that Fe is a metal, and if Fe is a metal, then it is going to make a cation. What is a cation? A cation is something that has a positive charge. But how many positive charges? We do not know. Now that is going to be determined by this Roman numeral. So when you see iron followed by a Roman numeral, in this case, that Roman numeral is 2. You will put the symbol of iron, which is Fe, and you will make it 2 positive. Then the rest of the problem is really simple. Oxide, we know, comes from oxygen because it ends with "ide", so it must be a single type of element. And oxygen, we know, belongs to group 6A. And so group 6A have 2 negative charge. So you have 2 positive, 2 negative, they cancel each other out perfectly, and the resulting formula you get is FeO. And that is how you figure out the formula for ionic binary compounds that contain a transition metal. Let's take another example. Just to make my point really clear, I've included the same 2 elements in the second example, but now instead of 2 Roman numeral, I have 3 Roman numeral. What does this mean? It means that this atom of iron, Fe, has lost 3 electrons, and as a result is now an Fe 3 positive ion. Once you figure out that Fe is 3 positive, and you know that oxygen is 2 negative. Now what do you do in this case when you have charges that are not even, right? So like in this case you have 3 positive and 2 negative. Anytime you come across a situation where you have 1 odd, 1 even, you simply flip them. What does that mean? It means that this 3 right here is going to end up here. This 2 here is going to end up here. And obviously you're going to ignore the positive and the negative signs. And so Fe 2O3. Remember, I got this 2 from the top of oxygen. I got this 3 from the top of iron, and I ignored the positive and negative sign. You can only do this if you have one odd and one even. Alright, so before we move on, let's take one last example of a metal that is not necessarily a transition metal. You will notice that lead belongs to group 4A. And I did not include group 4A in the list of oxidation numbers that I had given you in the very beginning. And that is for the same reason. Lead also does not have a fixed oxidation number, which is fine because this Roman numeral tells us the positive charge on lead. So lead is Pb. This right here means there's 4 positive. Chloride, we know, comes from chlorine, which is 1 negative. Please remember this, very, very important. This Roman numeral is always a positive number. It's always a positive number. Why is it always a positive number? Because this Roman numeral belongs to the metal, and metals are always positive. So that 4, or whatever that Roman numeral you see, will never be a negative number. So with that out of the way, let's figure this out. You've got 4 positives and 1 negative. To balance these out, you're going to need basically 3 more chlorines. So all of these make a 4 negative, and that's your 4 positive. And so the formula you get is PbCl4. Okay? Please, please, please do not confuse that this 4 is this 4. Okay? There's absolutely no connection there. This is pure coincidence that you got a 4 at the bottom and you have a 4 as a Roman numeral. So the formula for lead 4 chloride is PbCl4. And finally, we're over to the last segment of this video, and this is going to be over polyatomic ions. As you have already learned, polyatomic ions mean that your compound is tertiary. Okay, and so the tertiary ionic compounds are slightly different in you have got to be able to figure out the formula of the polyatomic ion first and then figure out the overall formula. So let's take an example and let's see how it's done. So here's an example in front of you. Iron 2-phosphate. I've purposefully taken an example of a transition metal just so that you get some good practice for solving these. Remember that if this was a group 1 or 2A metal, the process does not change. So let's get started. You have iron 2-phosphate. Now, when you say iron 2-phosphate, we know that iron is Fe and it is 2 positive. How do we know it's 2 positive? Because of this Roman numeral 2 right there. Now, what about phosphate? Notice what it ends with. It ends with 8. We have learned that anything that ends with 8, we have designated them as our base ions. Okay? And those base ions should be there in your list of polyatomic ions. And when you look at that list, you will find that phosphate is PO4, 3 negative. And now, there's a very small modification to what we've been doing so far. Just in the previous example, I told you that when you have 1 even, 1 odd, you can flip-flop them, which means this 2 will go to the bottom of the 4, and this 3 will go to the bottom of Fe. But there's a problem. You already have a number here. So, how do you differentiate this 2 from this 4? And luckily, there's an easy way to do this. All you have to do is write down the formula. So Fe, you get this 3, put this on the bottom here. Now you take this 2, but before you can write that 2, you have to use parentheses. So what you do is you take your formula, which is PO4, and you put it in parentheses, and then you put the 2 outside of the parentheses. What does this mean? It means that when you put the parentheses, that everything that's inside the parentheses is multiplied by 2. And so Fe3 parentheses PO4 2 is your formula. I want to elaborate a little bit on this being able to flipping the numbers. What does that mean? It means that when you have Fe with 2 positive charges and you have phosphate, which is PO4, that has 3 negative charges. Those are not even, right? They're not even. So you keep adding negative and positive charges until you end up with even numbers. And there you go. So you have 2, 4, 6 positives, 3 and 6 negatives. And that's how you got Fe3, PO4, 2. So those subscripts on the bottom tell you the number of ions of each cation and anion that's found in that chemical formula. And so those numbers are very, very important, and now hopefully you know what they mean. On to our next example, and that is that of calcium perchlorate. Calcium, as we know, is a metal, and calcium belongs to group 2A, and because it is 2A, we know right off the bat that it's 2 positive. Notice that there is no Roman numeral here because it is an A group element. So calcium is Ca2 positive. But what about perchlorate? It ends with 8, but it has this prefix per. We reviewed this in class, and from your list of the base ions, you should be able to figure out that chlorate is ClO3, 1 negative, but the fact that you have per, which means that it has 1 extra oxygen, and so your perchlorate ion becomes ClO4, 1 negative. Now you've got 2 positives and you've got 1 negative, so 2 positives, 1 negative, so you need 1 more negative. Now your charges are equal. You write the chemical symbols together. Remember, you have 2 of these, so you're going to have to put the polyatomic ion within parentheses, ClO4, and then 2 at the bottom. Where did we get this 2 from? Because we have 2 ions of perchlorate. And that is the formula for calcium perchlorate. Let's take another example and wrap this video up. So this last example is that of tin 2 carbonate. Tin is a transition metal. Well, it acts as a transition metal because it doesn't have a fixed oxidation number. You know that because it has a Roman numeral. So tin is Sn, and it's 2 positive because that's what the Roman numeral tells us. And then carbonate, notice that it ends with ite, which means it is not a base ion. The base ion would be carbonate because it would end with 8. So carbonate comes from the base ion carbonate, which is CO3, 2 negative, but because it is ite, it must mean that it is 1 less oxygen, and so CO3 would become CO2, 2 negative. And now it's pretty straightforward. You got 2 positive and 2 negative. They cancel each other out perfectly, so you don't need to add or write any extra number or anything. No parentheses needed. Sn, CO2. We were able to do this because my cation and my anion canceled their charges out perfectly without me having to add any extra. Okay, so hopefully this video uh, served you well, and I hope that you took some good notes and wrote down your questions on the side. Please make sure that when you see me in class, you ask me or ask your teacher, and good luck with naming compounds and writing formulas.